right? So this statement is not the right statement, right? But what would the correct statement be? What is in fact the expected weight of edges between A and B? Zero. So it's half time W plus 0. So the expected total weight of the edges between A and B is thus not the number of edges divided by 2, is the total weight of all the edges divided by 2. Okay, so that number will change. And now you put it here and say, what is this? Well, we know that this number can be at most the total weight of the edges, because the best solution can take all the edges. So now you have half the total weight divided by the total weight. Still half. It doesn't matter. That's the beauty of this method. And that's the beauty of all these things, that often the weights don't matter. That's not always true, but in this example it doesn't. Because the counterintuitive thing is that you think, oh no, these heavyweight edges, I really need to make sure they're in the cut. But if I pick it random, if I get them, I'll get half their weight anyway. It's not like I only get a teeny bit of the weight. I get the whole thing. And that's where the intuition is different, right? So you're thinking, I want to work hard, I want to find these 7, just pick it random. That's the beauty of randomization. It allows you to not to worry about some of these details. You could otherwise be very careful, like, oh yeah, take this weight, put it there, do that. Yeah. Okay? So this works for weighted graphs. Okay, let's move on. So is everyone clear on the basic concept of an approximation algorithm and how we reason about it, how we talk about it? So this is the basic template for what we're going to be seeing here. Okay? Okay. All right.
Just one question.
Yeah.
So it's just a randomized algorithm and approximation is approximation is in its outcome.
Yes.
Right.
Correct.
So how does randomized algorithm approximation algorithms different? Because in randomized also we are saying with some probability it's always correct.
But if you're wrong, you could be horribly wrong. So my answer, suppose I don't have an approximation algorithm. My answer could be the exact answer for this problem with probability 2/3. But when it's not, it's much worse.
Okay, so we are keeping bound on.
Here I'm trying to be more careful. Which is why you can talk about a randomized algorithm, for example, for a problem with a yes-no answer. With some probability I get the correct answer. But if you want to talk about approximations, that's why I mentioned this point, you can't approximate 0 versus 1. If you're not 1, you're 0. There's no ratio there. That's why you have to have an actual value. Okay? So the numerical value actually matters. So so the whole reason we do this is because it's often easier to get an approximation than actually solve the real problem. Sometimes the real problem is intractable, sometimes the real problem is just painful. So, again, and for some problems even n squared is too much, and you want to do better. And one example of what I want to show you is finding the median. Okay? It's a very simple problem. I give you n numbers, and let's write down. So let's call out some numbers. Some numbers between 1 and, I don't know, 50.
5.
5.
20.
E. There's always one of you. There's always one of you. Fine.
43.
Huh?
43.
LN2.
Huh?
LN2.
Oh, it's all smart asses. 2 more. 17 and 50. All right. Okay. So we have 1, 2, 3, 4, 5, 6, 7. Good. Nice odd number. Once we have a set of numbers, we can talk about the rank of a number, its position in the sorted order, if we had a sorted order. So for example, the rank, which I've defined here, what is the rank of 5? How many numbers are less than or equal to 5? And now whoever said ln2 has to now actually calculate the value. So what is the rank of 5? How many numbers in this list are less than or equal to 5? 2 or 3? 5, E, and ln2, I think. Yes, ln2. Yeah. Okay. Because ln2 is less than 1. So rank of 5 is equal to 3. Okay. Is there a number whose rank is equal to 4? Well, what's the number just above 5? 17, right? So 17 has 17, 5, E, and log 2. Okay. What 18? What 19? What?
Oh,
Where?
Okay, never mind.
There's no 18 in the list. Okay, what's the rank of 50? Okay. So of course the median is the middle of the list. But since we're talking about approximations, I want to have a number as an output. So I'm going to say the median is an element whose rank is, well in this case I should have said n minus 1 over 2, but you get, yeah. So is this here. So in this case the median is 17. And of course, you can find the median in linear time. You don't have to sort. This was one of the cool results in the early 70s. You don't have to actually sort to find the median. You can find the median in linear time by a process of divide and conquer called prudent search or decimation, or kill 1 out of every 10 Roman soldiers and etc. That's what decimation means, by the way. But that's what's used to find the median. Okay, so we can find the median in linear time. It doesn't get much better than that. Linear time, what more can you ask for? But of course we will ask for more. I want to find the median in constant time. I don't want to read the input. That's just too much work. Who reads the input nowadays? You get the TLDR from a couple of samples, and it should be done. Right? Who needs to read the whole thing? Can you find the median in constant time? And that's the question we're going to ask. So let's first define what it means to be approximate. Right? What is an approximate median? Because we're not going to find exact median. I think it should be very clear to you that if I miss even one element, that could be the median. So if I want to actually find the real median, I'm not going to lose in constant time. Because the minute you don't look at a particular element, the adversary makes sure that was the median element. By putting it very carefully. And there's a formal way to reason this. But can we find an approximate median? And first we define what it means to be an approximate median. We don't actually know what that means. The obvious way to define an approximate median is to find a number m tilde that is very close to the actual median. So its difference from the actual median is small. And we run into big trouble if we do this. So look at that example out there. So the example consists of numbers 1, 2, 3, 4, 5, 6, the number 1000, and the number 2000, 2005. The median of the set is obviously 1000. If you give me any number that is not the exact median, it's going to be really far from the median. Right? Its distance is going to be either 1000 or 994 or something really huge. And of course, I just chose these numbers. I could make them even worse. Right? I could set the small numbers down to minus infinity, the plus numbers up to plus infinity. I can make this difference arbitrarily bad. In other words, what I have shown to you is that finding a median whose value is close to the true median is the same problem as finding the median itself. Because no matter what, suppose you come to me and say, well, I have a 10 additive approximation to finding the value of the median. I say, oh really? Here are my numbers. Find your 10 additive approximation. Like, oh, actually, well, I just found the median itself. Because there's nothing else that even works. You say, well, I actually have 100 approximation. And I give you the same thing, and you see the problem. So what I've constructed is essentially your first hardness of approximation result here. You don't realize that that's what we've done. Giving this example, I've shown you that if you could compute an answer close to the median, you would compute the median itself. And therefore, if computing the median itself takes linear time, there's no way you can do this in less than linear time. It's like the NP hardness reductions. We just computed. So computing an approximate median by approximating the value of the median is hopeless. It's hopeless in that you're not going to be able to do anything any better than computing the actual median itself. So is this point clear? So this point, again, comes up a lot, especially in data problems, where you either can approximate the thing or the value of the thing. And I'm saying approximating the value of the thing is really hard. So let's not do that. Let's change the game. Remember that we defined the median as, in fact, a particular example of a value, the rank function, which is a number. So instead of trying to approximate the median value itself, let's try to approximate the rank, because maybe we want the median because we want to split evenly. And if you want to split evenly, maybe we can split kind of evenly, and then let the Marshall theorem tell us, that's going to be okay. So in that case, can we find an n tilde so that the rank difference number whose rank is similar to the rank of the median? And now our problem goes away because both these numbers, 6 and 2000, are very different in value, but their rank is very close to the rank of the median. So our earlier objection goes away. So see that pivot that we've done here, right? We've gone from saying I want to approximate the value of the median to approximate the value of the rank of the median. And again, when you do approximations, as I said, the first thing you have to do is define what the value output is. So that choice itself will decide what you can and cannot do. And that's a choice you make. Yes?
What about the objection of like values is still too far, we are still not approximating well enough?
The question is, what do you want? What is the goal here? If the goal was to get the value, then this is not going to help you. You have to do that, and you'll say, sorry, I can't do that, and you go back and you cry into your coffee and you run a later time out there. But if your goal was to use the median to split, and you're doing load balancing, then what do you care? So it completely depends on the problem. It completely depends on what you want to do with the answer. Whether you want an approximation, what kind of approximation you want, it depends on your problem. All I'm trying to show you is that there are choices you can make. And those choices can have an impact on whether you're able to do this or not. So you have to ask yourself that first question. What do I want this for? Yes?
Do you know if efficient quick sort implementations use this for the pivot?
Sorry?
Do you know if quick sort implementations use this for the pivot?
Oh, they completely use this. Because they completely use what we're going to say next.
Okay.
Absolutely. Because it's a waste of time to just compute the median later time. It's too much work. If you do that, then your quicksort would not be very fast. There would be too much overhead from that. It would be still n log n, but the overhead of computing the median would increase your constants by so much that it would not be worth it. And we're going to see how to fix that. So is this sort of setup clear that we've taken the problem, we've defined the notion of value so we can approximate. We discovered our first notion of value doesn't work, and so we've changed it a little bit. Yes?
So what intuition do we have? So right now we've said that, okay, we can approximate the median. But what...
We haven't said that yet. We have defined the goal. I haven't got a solution yet. I've just defined the goal.
Right.
The goal is to do this.
We've defined some metric.
Yes, some metric, very good.
But what we still don't have an inkling, is this even possible yet?
Absolutely, we have no idea if this is possible. We just know that that wasn't possible. We have no idea if this is possible. All we know is that wasn't possible, and the reason that wasn't possible does not make this not possible. In other words, our counterexample to break that argument doesn't break this argument. So it's sort of hanging on for dear life, hoping for the best. Okay? Okay. Let's try to come up with a solution. And here's a solution. Sample an element randomly. That's your median. This is the most brain-dead solution you could come up with. I just pick an element random and say, yay, median. So in this case, for example, I'd like 3. That's my median. That's going to be a random. And of course, this is terrible, right? But how terrible is it? Well, what's the probability we get the exact answer? That's 1 over n, right? The probability you pick the exact answer is 1 over n because only one of those elements is it. Odd, even, whatever. So that's bad. We don't like probabilities of success of 1 over n. We want probabilities of failure that are 1. But here's the thing, is it close? Can you get an answer can you say that this answer, even though it's horrible, is not too far away from the right answer, under a notion of far? And now let's think more carefully. So think of your input. Now this is where we're going to start reasoning optimal solution, right? If you imagine your input in sorted order, the median would be in the middle. We don't have it, but we can imagine it. So let's imagine the input in sorted order. Let's imagine the median point, and let's imagine a range of size n over 2 elements around it. So n over 4 elements in one. This, of course, by definition, gets you to the element of rank n over 4 and the element of rank 3 n over 4, just by construction. So I'm not measuring in actual like geometry distance, just counting in terms of counting number of points. That's what I meant by going that far out. So now we can ask the following question. What is the probability that the random sample you pick is in this middle range, which I'll call the good range, just for no particular reason? So, actually there is a reason, right? The reason I'm calling it the good range is that any element in that range is kind of close to the median in rank. It's not great, but it's close. It's closer than this for one thing. In particular, the distance of the rank is at most n over 4 by construction, because I'm going from rank n over 4 to 3n over 4. So any element in that set will have a rank difference from the median of at most n over 4. Okay, how many of them are there? There's a ton of them. Half the elements are in that set. So the probability of picking an element, m tilde, at random, that is close, an approximation to the median with n over 4 is at least half. And that's why a random pivot works for quicksort. Because it's a reasonable probability, you get a reasonable split. Because now if I do a split, if I was using this median to do splitting, my recurrence instead of being 2t n over 2 becomes possibly t of n over 4 plus t of 3 n over 4, which is still okay. It's not great, but it's not. And it's taken me how much time to do this? 1. I have not run the input. I've done one sample, and I get an answer that's not, that I can actually say something non-trivial about. Much more so than before. Yeah?
Why is it at least half and not just we have?
I'm being unnecessarily cautious. Yeah, it is exactly. I want to get rid of off-by-one issues. Yeah.
You're assuming that's sorted, right?
No, I'm not. That's the point. I'm imagining what the world would look like if it were sorted. But when I sample, I don't care if it's sorted. All I know is there is a good region in the middle, and my sample is going to go and pick in the middle. I'm using the sorting merely to reason about the size of my good set. I'm not actually sorting it. And that's where this whole weird twist comes in. I have to imagine the optimal layout without actually computing it. If I have to sort, then I'm done. Set log n. But I don't have to sort. This reasoning works regardless. What I'm saying is, okay, I go pick somewhere, boom. The middle region is where I want to be. That has a certain mass to it. It doesn't matter whether it's sorted or not, but the mass is still the same. Right? So in my example above, let's see, let's go back here. What I'm saying is that the middle region, so let's say, okay, so now n was 7, the median was, so let's say I want to go out to half. So let's say I take the elements, which would be this one, and let's go one up, which is 20, and let's go one down, which would be 5, and let's go one up, which would be 43, and let's go one down, which would be E. This set is not sorted, right? But it has 5 elements in my good range, which I've marked there. If I pick uniformly at random, the probability that I pick one of these good elements has nothing to do if it's sorted or not, right? I'm just using the sorting to reason about the quality of that set. Does that make sense? It's a very good question, but I'm glad you asked it, but that's how it works. So. Yes?
So would the cost function always be based on the rank of the number rather than the number?
It depends. Like I said, if you want to do this number, then you're dead. You can't do anything. Yeah. So it depends on the problem.
Can you do provable better on average by taking more than one but still a constant
Idea 2. Why take 1 when you can take 3? Here's my new algorithm. Take 3 elements. Why 3? Because I want to take the middle one. So we don't want to rest on our laurels. We don't want to be happy with this, somewhat not that great bound that none of you seem very enthusiastic about, even though I am. So we want to do better because I have a demanding audience here. So we'll take 3 elements and take their median. Okay? Now what happens? So again, we have the same quality we want to maintain, this n over 4 to 3 n over 4. And again, I want to reason about the quality of my solution. I mean, the probability of getting a solution. So I've fixed the quality. I want to be within the n over 4 error. So the only question is, can I jack up my probability from half to something much more than half? Right? You can think of this other way around as well. Okay. So now we have to think a little bit more carefully. when do we get a bad answer? So let's think carefully about this. Let's define the regions where bad things can happen. First of all, is the A region there, which are things on one side, and the C region there, which are things on the other side. The claim we're making, the claim that drives this algorithm's analysis, is the sentence right here. As long as you do not pick two elements in A or two elements in C, you're fine. So let's think through that. So let's first see if you do pick something there. Suppose you pick two elements in A. What's your median going to be? The median of those three elements, no matter where the third element is going to be an element in A. Because there are two elements in A, one thing is somewhere else, the median is the middle is going to be in A. And that's a bad answer, because that's outside our approximation guarantee. Similarly for 2 in C, it's going to be a bad answer. If you have 3 in C, it's even worse. But if you have only one, at most 1 in A and at most 1 in C, then you could have 1, 1, 1, in which case you're fine. You could have 1, 2, 0, which case you're fine. Or you could have 0, 2, 1, in which case you're fine. So the crux to analyzing this algorithm is to say what is the probability of a bad event, which is to say what is the bad event, and this is the bad event. 2 or more elements in A, or 2 or more elements in C. If we can somehow make sure that doesn't happen, we'll be okay. And now you can see how we're attacking this problem. We know that the bad event happens when you have lots of stuff on one side or lots of stuff on the other side. But these sides are small. You should be able to get lots of stuff on one side or the other. They're small sets. That's the whole point of them being small. The probability of landing in there is small. Let's do the calculation. What is the probability of picking 2 or 3 elements from A? Well, it has 1/4 of the set in it, right? So the probability of picking one element is 1/4. The probability of picking 2 elements is 1/4 squared, and that's it. If you want to pick 3, it's 1/4 cubed. Either of these two things could happen. I'm going to be lazy, so I'm just going to say, okay, let's add these two things. This is double counting, but I don't care. So it's less than equal to that. Similarly, this happens here. You get 5 over 64. So the probability that you do this bad thing is 5 over 32. Therefore, the probability of the good event is 27 over 32, which is now way more than half. Just by going from 1 to 3 and taking the median, you've jacked up your probability of success way higher for that same approximation guarantee. That, of course, I'm waiting for the next question. Yes?
So I guess it makes sense that you want to pick 3 medians, but what do you do with the 3s? Which one do you pick to be a final median?
Oh no, you pick 3, take their median.
Okay.
Their median is your answer.
Okay.
That's why the reasoning is working. Because you're saying take the middle of 3 elements. And that's why if I pick 2 on one side and 1 on the other, then the middle of those 3 has to be that element in the middle. It's going to be a bad element. And that's why I'm going to exclude these 2 cases. That make sense? Yes?
Suppose I take the sample space and divide it by 4, so that I get 4 sample spaces. I find a median of each of those sample spaces.
Wait, so you divide the space, how do you divide the space by 4?
Like say 4.
Sorry?
So like I divide the sample space by
Oh, just 4 groups.
4 groups.
Yeah.
And find a median of all those.
Yes.
And then, try to find the median which is based on these.
Yes.
Then I can get a probability better than that, like 27.
Sure, you can. You're doing more work.
But it's at least the more better approximation.
Right. There's a trade-off. I mean, obviously you can get the best answer by spending more time, right? If you spend little time, I get the perfect answer. The game is the trade-off. How little work can you do and still get a decent answer? You're going to do a bit more work, you're going to get a better answer. I'm going to do more work, you're going to get a better. You see the trade-off here. You can always jack up one side, but the other side, you pay the other side. Yeah.
And of the 3 medians, you take random element?
No, there are 3 medians. There's 3 elements.
Okay, 3
you
elements.
pick at random and take the median.
So you will sort these 3 and then take the median?
No, I pick 3 elements at random. I don't solve anything.
Okay.
Okay, let me, I'm a bit worried now because I think I didn't explain the algorithm correctly. The algorithm is this. Pick 3 elements at random. Let's go back to our input. Here. I pick 3 elements at random, 5, 20, and E. I take their median, it's 5. That's my answer. Done. I take 3 time steps to do this. I don't do anything clever. I don't compute medians. I don't divide things up. I just take 3 things. This is constant time, this algorithm. Is that clear? There seems to be some confusion of what exactly the algorithm is doing. I'm not doing anything else. I'm not sorting. I'm not doing anything. I'm just taking 3 elements at random. That's the power of this method. Okay. So back to the analysis. Yes.
I think it should be 1 over 16, not 5 over. Take 3 elements into A, it's equal to the situation. You already can't. You don't need add situation. You take 3 elements.
Oh, completely. I was being lazy. I was being very careless. This should really be a.
So actually,
That's an equal.
yeah.
But this is the thing we do, right? I'm trying to upper bound the probability of a bad event. You know. Yeah, you're right. Absolutely right. You have to. One thing I will say though, you must get used to being correctly sloppy. In other words, as long as your inequality is in the right direction, it's okay to be sloppy. Because if you start trying to be very accurate, that's great, but you'll go crazy with some of these calculations, especially in probability. So the trick is to know how to simplify in the right direction. That's what I mean by correctly sloppy. It's okay to simplify by giving a crude upper bound. It's not okay to simplify by giving it a lower bound. Because I want to upper bound the probability of a bad thing happening. Yes?
So if we wanted to tighten the bound around M, would that be opposite just by taking a few more elements?
It would. In fact, you can take 5 elements and do this analysis all over again. You could take 7 and do it all over again. And there will be a question about this. Yes. And that's where these tailbones are going to be thinking we've been talking about will come into play. That all these sampling tricks, yeah, as you, again, and there will be a trade-off. The more samples you take, the better your bound will get, but it will take more time. Conversely, you can say, well, you know, yes, I know the probability is better for 1/4, 3/4 approximation. If I'm willing to be only half in my probability of error, how narrow does the bound get? So the whole confidence. So this goes back to the whole issue of confidence bounds, right? You can give a confidence bound of 95% with certain probability. You can give a confidence bound that's weaker with a larger probability. There's a trade-off between the approximation error and the probability of that happening. This is one point on the trade-off. If I want 1/4 n over 4 approximation, I get this probability of success. One more that. But this is what I can actually show. That the probability that the rank is less than 0.1 n. Oh, sorry. That's not right. Let me fix that. That the probability that the answer I get is more than 0.1 n away from the true answer is less than half. Which is another pointless trade-off, right? So there's one probability of getting within n over 4, which is very high. If I want to say, well, what's the probability I get a lot closer? Of course, the probability goes down, but it still stays. So this result I showed you is actually a trade-off. It's not a single result. It's a whole spectrum of results depending on what probability you want. And the way to prove this is you can say, well, instead of saying n over 4, I just move out delta in one direction, delta in the other, write down all my analysis in terms of delta, and then you can get different trade-offs between the probability of error and the actual approximation you get. So that one result gives you all these things. Okay? Does that answer your question? A little bit? I mean, this is, by the way, without doing anything else to the algorithm. The same algorithm can be viewed as giving you a whole spectrum of behaviors. And if I now throw more points, I can get even better trade-off. So let's recap, right? So, if you have running time of O of 1, you can pick 3 elements, complete the median. This compares to the exact median, which would be O of n. And again, like I said, the n of approximate median takes only constant time with probability 27 over 32. And like I said, you can do even better and by taking more samples. Okay? All right. Yes?
So are we in approximation algorithm right now? Because
yes.
when we're wrong, we could be wrong by a lot, right? And that's not something we want.
I see what you mean. Well, yeah, no, okay. So again, these lines are not as bright as you're making out. I mean, what I'm saying is that when I say I'm designing an approximation algorithm, I want to give an answer that's close to the right answer. Right? That's what I'm doing here. Yes, it also has a randomized element to it. The next one won't. But I'm just giving you this. I mean, the point here is this part. So is this part here. This part is just when you add a randomization layer on top of it. That's separate. They're all approximation algorithms. Some of them have to be randomized, some of them have to be deterministic. But it's like, you can make a little, you can make a little grid if you want, right? So this is randomized, deterministic, exact, approximate. You can, I'm just dealing with everything here. I don't really care whether it's here or here or not. Okay. Questions before I move on?
So you're saying that more than half the time you're within 0.1 after.
Which is a pretty good estimate. And again, if you do more work, by taking more samples, you can get even better. Yeah?
Doesn't that seem like too good to be true? Just 7 over 32.
Life is good when you have all these tools in your hand. So why do you say it's too good to be true? Are you suspicious? Is that something that you think is... So why do you say too good to be true?
Because first of all, the set is not ordered. You get picking elements randomly.
I know, it's crazy, right? How on earth could this possibly be true? It's just bizarre. I completely agree with you. It is very bizarre, yet it's true. That's exactly what I want to try to convey. There's a lot of magic here. And it's coming from the fact, let me try to explain this to you. If I want to approximate the median rank, I want you to think about it this way. If I'm saying I want to approximate the rank up to 0.1 n even, okay? I'm saying that there are n over 10 elements, or n over 10 elements on either side, n over 20, n over 5 elements that are acceptable to me, right? Okay, let me say this another way. 1/5 of my data is an acceptable answer. Okay, now does sampling seem more plausible? If a 1/5 fraction of my data is a plausible answer, it seems real. That means the probability of picking something that's good is what? 1 over 5. Okay, now go back to the homework, right? There's something that can happen which is good, which is probably 1 over 5. How many times do I need to pick to get something that's good? 5 times. That's the intuition. When you have enough witnesses, when you're trying to find hay in a haystack, it actually is okay. It's not that surprising. But when you have to sort of reprogram to think, okay, what are the set of, how many witnesses are actually candidate possibilities here? And that's why, by the way, approximating the value was so much harder. There was only one witness that got you what you wanted. The median itself. Everything else was terrible. Randomization is not going to help with that. And you can't approximate. There's just not enough structure in the problem. So that's what you're looking for in these problems. There's enough structure, enough witness structure to do it. And then, you don't know ahead of time whether it will. And somehow you have to, often you only realize the structure is there a year after proving the result. But that's what's really going on in these kinds of problems. That's why it's not as incredible or not as too good to be true as it seems on the surface. Because there really is enough witness structure there to find the answer. You just have to say it the right way. But I like that question. It is important to sort of check your intuition and say, okay, this sounds weird. And try to understand why it's weird. And if you still can't get the answer, then maybe something wrong. Okay. Next problem. Estimating large frequencies. Again, if you've taken data mining, you may have heard of this problem. So in our previous example, right, in both examples in fact, we wanted to use approximation to make things run faster. And as I said, that's not always the resource you care about. Sometimes you care about other resources. In this case, we care about space of the resource, not time. It's like with hashing, we want a small space. And so the question is now, can you use the same ideas of approximations to reduce the space of your computation as opposed to reducing the time of your computation? And this again comes up a lot in sketching, when you're doing sketching and streaming and all, you want to reduce the data size down to do something with it. Of course, it helps you in time, but the main thing is it helps you in space. So let's take a problem. I have a stream of m items. Okay, they're drawn from a universe of size n. So let's say n is equal to 10. Give me a stream of items from 1 to 10 that they should have repetitions. Call numbers. Integers from 1 to 10.
One.
7.
3.
Fine, we'll go MATLAB.
5.
1.9 repeated.
Anyone?
10.
Okay. Of course, once you have a set, you can say what is the frequency of an item, right? So the frequency of 1 is equal to 3, the frequency of 7 is equal to 1, the frequency of 10 is equal to 2, and so on, right? And the problem we're asking is, find the top k frequencies. This is a classic problem that's become very important in all kinds of data things. You think of it as attention focus mechanisms. You want to find the most frequent things, the most popular things that you want to pay most attention to, right? The top k, whatever top k means. Right? These could be, again, these frequencies could be coming from many sources. The point is you want to find the top k. So my answer, if k was 2, my answers would be, so if k is 2 here, my answer is going to be what? What are the things that are the top 2 frequencies? It's going to be 1 and 10, or 5 also, maybe 5. So any two of these three, well, 1 and any two of these two would be fine, right? Okay. Problem clear? It should be, it's trivial to see that if you have n space, you can do this. Just maintain the buckets. Count them. But I don't want to use n space. I want to use much less than n space. And this brings us to a puzzle that many of you have probably heard of already. This is a classic, Google interview question. So pay attention. I give you m items, and I give you a promise. There is one item that appears strictly more than m over 2 times. So it's a majority element. Find it in constant space. So you can't store the input. You have constant. In fact, I'll give you 2 units of space. Find this. How many of you seen this problem before? 1. Oh, yeah, that's good. That's great. That means you can think about it. Okay, I'll give you a few minutes. This is the point of the question. So again, is the question clear? I give you a bunch of numbers. They're coming by. That's whizzing by like this, right? And I promise you that one. Find it. Yeah? Hey, wait, you know the answer. You said you heard the problem.
No, but just to clarify,
okay,
on the
good.
screen you can only see one item and then you can never look at it again.
I'm not even saying that. I just said you only have memory to store 2 things. Yeah. But yeah, actually it's also important that, once it's gone, it's gone. Yes. Yes, you're good.
What if you say the frequency is 2 and
Wait, what do you mean the frequency?
it comes 2 times?
Element comes 2 times?
Yeah.
Okay.
And start with that and store that element in the frequency.
Okay, fine.
And each time something comes greater, you start building it.
Some?
Each time you get a new element, and you know the frequency, the number of times it's coming. Start updating it.
Okay, so I get 1. Then I get 1. So okay, I've got 1 as the frequency 2.
Yeah.
Now I get 3. Now what do you do?
Don't update it.
Don't update it, just leave it?
Oh, so you get 1 element each time, is it?
Yeah. Yes.
Pick a number randomly and probability that you are correct is half, more than half.
Yeah, but random.
I don't know why you're all laughing. I'm thinking. You should be thinking too. So pick a number at random. Okay.
Because it appears more than m by 2 times. So the probability that you are correct is greater than.
But you pick any element at random. From which domain?
You're given m items.
Sorry?
You're given m items.
Well, I'm not given the items. I know that they come from a certain domain. So in other words, our domain was 10, right? So you're saying pick an item at random element from 10, at random from 10. Then what do you do?
Yeah.
Okay, so so the algorithm is pick an element at random from the domain. Okay? Since there's a majority element, there's a probability of more than half of picking the right one. That won't work. You see why, right? Okay, yeah.
Yeah, so
What if as you're going through the list of items, you count how many times you consecutively see that current item, and if you store the highest number that you see consecutively?
So can you give me an example? So I get 1. My first number is 1.
Right.
My second number is 1.
So if the next number is 1, then your consecutive counter is 2.
Now I see 3.
Then you just store 2 as like a variable.
Then I see 4.
Then you just stay with 2.
And I see 5.
Well, you go until you get another number that's consecutive more than 2 times.
Yeah, but how do you remember that? You already used up your memory to store this first number.
Well, I mean, you would have basically just 2 variables, one to store the counter and one to store...
Right, so you've already stored your number 1 and the counter 2.
Right.
Now 3 comes in, what do you do? I have 2 units of storage. I have 1 in and I count 2 and I have 3 comes in. Now what do I do?
Well, I guess you need 3. You need the one, you need to keep the previous number.
But I can't keep that, and that's too big.
Well, you still only need a constant amount of them. You only need the current number and the number you've seen before that, and how many...
Okay, so suppose my numbers are 10, 9, 8, 7, 6, 5, 5, 5, 5, 5, 5, 5, 5, 5. Now you have to store everything before to get to the 5, 5, 5, 5, 5.
No, you wouldn't, because like so when you go 10 to 9 to 8, you wouldn't need to remember 10 because you know that it wasn't consecutive.
Suppose I got 10, 10, 9, 9, 8, 8, now what?
And then any of those...
But what does your algorithm do?
Well, I mean, it would just remember the first time something was repeated.
So, okay, so I give you 10, 10.
Right, and so...
Okay, you got 10. Now I give you 9. What do you do?
You'd just be storing it. If it's a bad algorithm.
No, it's not a bad algorithm. What I want you to do is not play cat and mouse with my counter examples. I want you to give me the algorithm. I'm trying to force you to define your algorithm fixed without changing it as I give you inputs.
Right, okay, so you need to store the number you're currently on, how many times you've seen that in this consecutive. You need to store the number that you've seen the most and how many times you've seen that number.
But the most, that's the problem. How do you see the most? You can't do that. You don't have enough.
I've seen the most so far.
But that's, so far is the same as everything, right? I mean, that means that by the end of the run, the number you've seen so far the most is in fact the most frequent item. You don't have a way of doing that. We don't have enough information to store the number we most frequently see.
I mean seen the most consecutively, not the most period.
Right, but if I have a whole...
Is the number that is consecutive the most is more likely to be the number that occurs most in the list.
Yeah, but this 10, 10, 9, 9, 8 example is going to confuse your algorithm because I might slip in 10, 10, 9, 9, 8, 8, then 10, 10, 9, 9, 8, 8, then 10, 10, 10, 10, 10, 10, 10.
I'm not saying it'll always be correct, that's not the point.
Oh, but that is the point. I want to be correct.
So we're still talking about approximation?
We are, but they want to be correct. In this case, in this particular problem, I want to give me that answer. But no, I think you're on the right track here. This is a good, so those of you who are too busy talking and not listening, his idea of what is going to be the solution. I'm just trying to sort of flesh it out a little bit more, see where it's coming up. So I don't even know which order, so we'll start here.
I don't know if this counts as cheating because I saw something similar in data mining class.
That is cheating. yeah, you had a hand up. Yeah.
Can I just pick 2 numbers at the same time? If these 2 numbers same, we just use this number. If these 2 numbers are not same, we just pick it again until we got same number. So we regard it as that way.
So suspiciously like my next slide, but we'll get to that.
Really?
Yeah. Any other hands up? Yeah.
Please show min and max. Please show min and max, and we select randomly from that defined parameter.
How do you get the min and max?
So.
Oh, you compute the min and max.
Yes.
And you pick one of them at random.
Yeah. So we have 2 storages. One you.
Okay, so my input is 1, 5, 5, 5, 5, 5, 5, 5, 5, 5, 10.
Yeah.
So your answer will be 1 or 10.
Yeah, so you take a number randomly from between 1 and 10. So
Oh, randomly between 1 and 10?
Yes.
But that's just like the original one, just
yeah.
pick it random.
So it's just the domain is defined now.
But I gave you the domain, it's 1 through n.
Okay.
Okay, yes.
So does this guy have passages?
No.
Okay, so I have an idea. How about we bubble sort it with... Like,
You can't, you only have 2 units of storage.
I know, but so the way I do this is I start at the beginning, I swap the 2 elements.
Then you,
and I swap
no, they're gone, that's gone. You can't write down. You only have 2 units of storage.
I only have 2 units of storage.
Completely, no, you don't even have the input. You don't have the inputs at all. You can't read the input either, it's gone.
So I only have 2 units of input, and I can only read the input once.
Yeah.
Okay, that's different. Then.
Exactly. Yeah, Paul.
Is there a time?
Nope. Don't care.
So I would just, first one, only then the second one.
You can't, you read it's gone.
But you agree,
No, you can't.
but it's not.
That's what I'm, okay. Yes. One last question and we'll move on. Yeah.
So in the 2 units of storage, in one of the units, I just make
Everyone, please.
the number of times a particular item is being stored, and I have a promise that it appears more than m by.
But which one do you keep track of?
So the first
What is 1, 2, 3, 5, 5, 5, 5, 5, 5, 5, 5, 5.
okay, so I have 1 in there,
Yeah.
and then I keep counting the next 2.
But I don't see 1 again. Its count is going to stay 1. I have to have a way to switch, to change my mind. Okay, so think of it this way, and you probably can come up with a solution yourself in any one of different ways. But here's a way so after many years of knowing this algorithm and the solution, I had to come up with a different way of proving it for other reasons, and so there's a different proof altogether, which is kind of, I don't know, I think it's interesting. So think of it this way, look at your sequence, right? I promise there's a majority, right? So if there's no majority element in the first part of the sequence, there must be a majority element in the second part of the sequence. Right? So, in other words, if everything balanced out nicely in the first part, so the majority element didn't show up, then all of its extra frequency has to show up at the end. So it must be the majority element there. Right? Because it occurs more than half the time. So if it's less than half here, it has to be more than half there. Okay? Just keep that in mind. So if I have a sequence, and I know that sigma is a majority element, and sigma 1 does it, then sigma 2 must have a majority element. And the key point here is that, and this is something that a couple of you were alluding to, the first sigma 1 can be of length 2. This is true for any sigma 1. So you had you're both talking the same thing. Imagine I have just 2 elements in the first set. If I take 2 element sequence, can I tell if it's a majority or not? Well, if it's the same element occurring twice, then yes, it's a majority. If it's not, then it isn't. Right? Yes? Okay. I just said if sigma 1 doesn't have a majority, then sigma 2 must have the majority element. So if I read 2 elements and they're different, it doesn't have a majority element, I can ignore it completely. Just throw it away. So if I take the first element, take the second, and they're different, act as if they were never there. They cannot be part of my answer. Okay? Because if it doesn't have this thing, if they're different, they don't form majority, and I just argue that it'll show up later on. So, in other words, if my majority element was 1, and my first 2 elements are 1 and 5, I can throw them both out. 1 will show up later. If the majority element was 1, the 2 elements are 5 and 6, I really don't care. But either way, it doesn't matter. If the 2 elements are the same, then maybe this is a majority, and we should keep its count. So in the case you're saying, you see 10, 10, keep the 10 and keep its count. That's exactly right. You should do that. But what do you do next? That's the key. Okay. So now you know you have 2 elements that are the same. What would make that sequence no longer be majority? If I saw 2 more things that were not that. Right? Well, how do I keep track? Well, I see the next element. If it's not that, I subtract it. So I saw 10 2 times. The third element comes in, it's not 10. So now my score is 2 to 1. So I reduce it. 1 extra over majority. If I see a new element that's not 10, it's going to go down to 0. And then I can ignore this whole sequence. And start all over again. So this is the algorithm. You have 2 storage, you have the storage for the item itself and the storage for its count. You read the first element. If it's whatever it is, you increment it. If it matches what you have, you increment the count. If it doesn't match, you decrement the count. If the count goes to 0, reset and start all over again. That's what this last step is. And return the element. That's it. You are guaranteed to find the majority element. Yes?
So this is a constant space because your count uses logarithmic bits?
Oh, yes, log bits. But apart from that, the words, log words of the input. I mean, it's constant number of words of the input. You must be a complexity theorist. Because the only people who care about that. So yes, but yeah, words of the input, yeah. Now there's a proof, and this is the proof here. I don't know if the proof is as interesting as the reasoning that I was just giving you. But this is a proof. Namely, if you do return some item, okay, and it has some true frequency, right? It's going to return some number in the counter which is less than its true frequency. Because I count it, but I also decrement things. So the value I return for the frequency of this item is never more than its true frequency. It's always less. But how much? It turns out its reported frequency is at least this minus some. It's close to this. So the difference, here's the approximation. The difference between this and the true value is not very large. Why? Think of what's happening. Every other element is going to try and reduce this element's frequency, the one that I returned. It had frequency Fi. I don't know what it is, but imagine I have this Fi again. Every other element is going to try and decrement that count by the second step. So the number of decrements it could possibly receive is as much as n minus its frequency. So its actual frequency reported will be its original frequency minus all the decrements, which is 2Fi minus n. But we said Fi was more than n over 2. So there's going to be this element, if it was a majority element with our frequency more than 1, everything else with our frequency of 0. So since I reported it back, it had a frequency of at least 1, which means it had to satisfy this property, which means it was an element that had a frequency more than n over 2. I just told you there was exactly one of those. It has to be exactly one of those. That's your answer. So again, the proof is a little bit twisted. But the basic idea is that you can forget an initial prefix where you don't have a majority, and that's keeping track of that by doing that forgetting step. And the last thing I want to say before we go is, this is the formal guarantee. That the error of the approximation is at most n over 2. It's a terrible approximation, but it's enough for the majority argument. And next time, we'll talk about doing much better than this. Okay? So sorry I ran over a little bit, but we'll continue. Yes? How will you store it?